Okay, everyone, welcome back today. We're going to be looking at a data-heavy project. This is going to be using a standardized data feed to be able to access global bike share information via a URL-based API, and then visualizing that data in TouchDesigner. So this is the project. What we're looking at here are real-time ride starts for right now just New York City, but as I'll talk about in a second, we'll be able to use this same process for any city that is supported by this standardized data format, which is most of them. So as rides are started and bikes are unlocked, those rides are then plotted on this map in real time. This is going to be coding heavy, so what we actually have is a Python program that is running continuously as a separate process, and then we're passing that data, including the new rides, from Python to TouchDesigner using OSC. I will also be talking a little bit about how I've been using ChatGPT or CodeGPT VS Code plugin to help me with development. Basically just showing you the workflow that I've been using for the last couple months, which may or may not give some helpful ideas. So, like I said, we're going to be really focusing on the data for this one, less so on the visualization, less so on the kind of interaction side of things, but as I've written about, data is really just another observer for our projects, so I think there's a lot to be learned. Now, with that said, we can get into things. I'm actually going to come back to TouchDesigner, but we are going to start completely in Python today. So, let me get rid of all of this, and what I'm going to do is actually just open a new VS Code and just get started directly from that. Okay, so I will do File. I'll open a folder. I will create a new folder here for this project, and that will be Global Ride Share Data Tutorial. I will select that folder, and now we will have a fresh workspace for this project. So then I'll just right click over here. I will add a new file. And what I'm going to be looking for, or what I'm going to be adding in this file, is actually a Jupyter notebook for us to get started on. I find it a lot easier to prototype and demo some of these scripting methods using a notebook because you can get your output a lot faster and just be able to see kind of some feedback on your techniques. So we'll call this sandbox.ipynb for IPython notebook. Hit enter, and then in VS Code you should just have a Jupyter notebook that is ready to go. I guess it's worth mentioning my Python distribution, which is Anaconda for Python. I just have the basic default installation. If you guys don't have Python installed and set up, I recommend you do that. I'm going to be assuming for the duration of this tutorial that everyone has a working familiarity with Python, even if you don't know it super well, and has the environment and environment or text editor set up. Obviously, I'll be using VS Code, and a lot of the workflow is going to be based around using VS Code. So you're welcome to use whatever text editor you like, but you may not be able to follow along completely. So, with that said, we can then start to look at our data and understand a bit more about what we're doing here. So, I started this project because I wanted to find Citibike data for my home city of New York. Citibike has a great data room. You can download historical data here for any month going back to 2013, as well as a real-time data feed, which is published in this general Bikeshare feed specification format. And then we can get the feed here. Now, this may look crazy and difficult to parse, but it's really not that bad. All this is doing is giving us a list of URLs that we can access to actually get the underlying data. So to understand a little bit more about that, we can dive into the general Bikeshare feed specification format. And this is what's going to allow this workflow to be used for pretty much any city or Bikeshare network that supports this feed specification, which is pretty much all of them. So, this is, again, the actual feed specification. If we click on systems.csv, we can see here a list of all of the Bikeshare systems that support this feed. So there are 820 of them across the world, from the US to UAE and everywhere in between. Czech Republic, Berlin, London, you name it. There seems to be a Bikeshare service that supports this data feed. So we can find the New York Citibike service. Maybe I'll just Control F Citibike, and we are now back to that same feed specification that we accessed directly from the Citibike website. So these take us to the same place, which is super helpful. So you can definitely dive in to more about this specification system if you're interested, but it's not super important beyond knowing that the specification system is standardized, which is what's going to allow us to use any of the URLs we want for our endpoint with just a little bit of modification. So the most important part, and really the only thing pertinent to us, is that this feed specification dictates that datasets should be published at an easily accessible permanent URL. That's great because it means we don't need an API key, and we can use built-in Python libraries to create URLs and then access those URLs programmatically, taking the responses and saving them to use later. It goes further to say it should be directly accessible without requiring login, and that it must have an entry in the systems.csv file, which is the list of supported systems that we already looked at. It also will go into file requirements, hours of operation, all of this stuff. But the main thing for us is that they should always be available via a permanent public URL, and that URL should be accessible without requiring login. So that's great. Again, systems.csv file will give you all of the different possible Bikeshare networks. When you select one, and I'll zoom in a little bit, when you select one and get the specification for your specific city of interest, you will see something that looks like this. Now, there are several different endpoints for each city. Um, First things first, at least for the New York Citibike one, we have English, we have Spanish, and we have French language options. So I'm obviously going to be using the English option, given that is my native language. Um, so you really just have 3 sets of duplicated feeds for each language. We can then briefly look at each of these. So this will be system information. That tells us high-level information about the system itself, Citibike in New York with a phone number. Not super helpful to me. Um, so next one would be station status. Or sorry, that's system information. So the next one will be station information. And here we see that we have a list of stations, and we'll be formatting all of this and making it easier to read in a second. Right now, I just want to kind of give a general sense of the data we're working with. So yeah, this will have a row for each station. That station will have an ID, a name, a lat long coordinate, and some other information like capacity and stuff like that. So the next one can be, or will be, rather, the station status. So this one is going to be the real-time update that we are most interested in for this project. So it'll show you for any given station what the number of available bikes, the number of available electronic bikes, the number of docks, whether or not it's active, whether or not it's actively renting, out of service flag, and a couple other pieces of information. Free bike status. For New York City Bike, we don't have free bikes. Those are the ones that don't have docks that you can just like leave anywhere. So that's just a blank JSON for us. System hours, pretty self-explanatory. Calendar, also pretty self-explanatory. And then regions. We'll take a look at this just for illustration's sake, but we see that this really just breaks it down into boroughs, or not even really boroughs, just some superset of boroughs, so not really helpful to us. And then system alerts. I don't think we really need either, but we can take a look just to be sure. Yeah, we don't. So the two that we're going to be interested in are station information, which is going to give us high-level info about our stations, and then station status, which will have the real-time data for each station. So now that we know which URLs we need, which is going to be this station status .json and then the station information .json, these are the two that we will then use Python to create a URL for. So back to my Jupyter notebook. In VS Code, I'm going to press this toggle panel button and get my below panels down here. Now, if you have Python installed, you want to select a Python interpreter, so you can use the command Shift-Control-P to bring up this command palette, and then if you don't see select interpreter, you can just type in select interpreter. I'm going to use just my base Python installation. Again, if you have Anaconda installed and followed those installation instructions, you should be able to use your base environment as well. If you're comfortable with creating virtual environments and want to do that setup and have a dedicated environment for this project, for sure, go do that. I'm going to skip that part right now just to keep things as minimally technical as possible. Then I will just open a new command prompt here, and we'll see that my base environment is now activated, uh, and so I am working within a Python context. So first things first, we need to actually be able to read our data into Python. So we need to define a Python function to hit that endpoint. As part of this, I'm going to be showing how a GPT assisted workflow can help with some of this. So let's just try with this station information URL to ask our Code GPT plugin, which I guess, by the way, I have the extension. So if you just search Code GPT, then there's this official Code GPT function that has 632,000 downloads. So I would recommend probably using that one, although I guess there are some other ones. This one's working fine for now. So anyway, I will just ask it, write me a Python function to query this URL endpoint and save all information into a pandas data frame. Now, I happen to know from experience that pandas is going to be a helpful library to use for this type of data visualization. Right now, we just want to get it into a nice, pretty frame. But if you didn't know that, what we could do instead is actually start with a question that's like, what is a good Python library for displaying tabular data? What is a good Python library for displaying tabular data for analysis? Okay, it's telling me that Pandas is a good library. I guess I will apologize if I can't zoom in as much. I didn't really think about that. Let's see. No, it does seem to be working. That's good. So hopefully this is easy enough to see for everyone. That looks like it should be. And cool, yeah, so it's telling me that Pandas is a great library. So now I can say, write me a Python function to query this URL endpoint and save the resulting data in a Pandas data frame. And then I can just paste the URL. Oops, paste the URL here. HTTPS gbfs dot citibikenyc.com/gbfs/n/station underscore information dot JSON. Okay, and we'll notice that they're telling us we're using another library and are writing this code for us. So now we can just put our cursor here, insert this code, and then use Control Enter or Shift Enter. Make sure you select the same Python environment, so in this case our base, and then using B to add another cell, we can call our new function And now we can see that indeed we're getting this same data in a much nicer, easier to read format that looks like this. We can set it equal to something like a variable by saying df equals this function, and then we can look at just the first 5 columns by using df.head. We can also look at the shape to see how many rows and columns we have. So we have 1900 rows or 1900 stations and 16 columns of data for each station. That is pretty good. Definitely helping us get started. So I will just print the head again so that we can see our data a little bit. And from here, we can do some light processing to get the data that we need. So first things first, we want to just extract the columns that we are interested here. So to do that, we can do something very simple, like df equals df, and then to extract the columns, we can just use a double list and put the column names that we're interested in inside this list. So for example, we'll want our station ID as a unique identifier. We'll want our latitude, we'll want our longitude, we'll want the maybe station capacity, and then you can take the geo ID as well. Or rather, sorry, not geo ID. Take the legacy ID in case we need it. The reason that you would need this is if you're trying to later on use some of the historical data, which I'm not going to get into at all for this tutorial, but as I showed you before, the historical data is all available on the Citibike system data page, and most other bike shares are also going to have this historical data up there. I was looking at Bikes earlier, and I noticed that they had the system or the historical data available for download as well. I believe that is also part of the general effort for those bike systems that are using the Bikeshare feed specification. However, it's not mandated, so it might not be possible to get historicals for all of them. In any case, that's why the legacy ID can be helpful in case the ID system changed at some point over time and you're looking to use historical data that includes the old IDs. Anyway, we can then use Control Enter or Shift Enter to run the cell. Control Enter will run it and not move. Shift Enter will run it and then move. We can see that then if we run our second cell, we're now selecting just the columns of interest to us, which makes it a lot easier to view and process the data. So that's great. One other thing that we should definitely do is use the latitude and longitude coordinates to create some normalized XY coordinates, because our lat and long are going to be, in this space based on wherever geographically you are. But inevitably, when we're rendering, we're going to want that to be in just a nice XY format. So what we can do is just use a couple simple functions to create minimums and maximums for each of those, and then apply some normalization functions. So first we have to find the min and the max for each of these stations. We can do min lat is going to be equal to minimum, and then we'll use a list comprehension. I for I in df, select the column latitude if I is greater than 0. So it's worth noting this I is greater than 0 is going to basically just exclude anything that is 0 or negative. That's fine for me because I'm working in a latitude, or like the northern hemisphere, where the latitude's always going to be positive, and I know that. You should check, verify your local lat range, may need to update I greater than 0. The reason that I had to add this was because some of the data had lat or long that was undefined or 0, and that was causing some issues with my visualization. So now I will just copy this and replace min with max. And I'll copy this one more time, and I'll call that min long. Change the max back to a min, select the longitude column, and now because my longitude is going to be negative for all of the values, I'm going to use -0 for that comparison, and then I'll use, or sorry, less than 0, and then I just have to put my max down. So this will be one area that if you are using a non-New York data feed, you'll have to change that and make sure that this is set up to whatever data you're using. So before I go on, I'm going to just clean up my notebook a little bit. I will cut and paste this code. I will click outside of the cell, just click out here, and press B. That'll add a cell below. I'll paste my function here, and then I'll add a quick comment and say function to grab all station info, and then I will again add another cell below, and this will be some utility functions. One of the utility functions that we'll need is going to be clamp. And so our clamp, we can define x, a, and b, and we will just return max of, in this case, a, min, x, and b. And so this will return a value that is always going to be between a and b, based on whatever the input x is. We can then define a map function, which will take in 5 inputs, x, a, b, c, and d. And then we can define our function y equals to c plus x minus a over b minus a times d minus c. And this is just the super standard mapping function. And then we can just return a clamped version of y between c and d. So now whatever we put input for x, it'll map it from this range AB to the range CD. Whoops, to the range CD. That's like the map function in processing or whatever. So we can now run this cell and have access to these functions. We'll run this cell again since we pasted that code. Now we can use our new functions and apply them to our data frame. So we'll add new columns to our data frame, and we will do that by using this assign method, and we'll call it x. X is going to be equal to df.apply, and this is going to be then applying the function that we're about to state to that entire data frame and create a new column with the output. Lambda row. So then what we're doing now is using a lambda expression. So whatever is coming after this lambda expression is going to be abstractly used for all instances that the function is applied to. And then we'll map that row's latitude value from minlat maxlat to the range 0 to 1. And actually, we can default this C and D to 0 and 1, so that if we don't pass arguments for the map2 range, it will simply default to 0 and 1. So all we have to say is map our latitude of each row to the minlat and the maxlat. And then inside of the assign, but outside of the apply, we want to put axis equals 1 so that we are getting new columns. All we have to do is change this to Y, change this to long, change this to long, like so. Now we can run this code again and run our next block, and we can see our X and Y columns are nicely added. And you're welcome to verify that the normalization is occurring correctly as well. You can obviously just do that by printing these values and doing the math manually. Yeah, I'm not going to verify it, but you're welcome to. So now we have a data frame for all of our systems, or station systems, stations that include a normalized X and Y coordinate for each of the latitude longitude pairs. That will allow us to easily plot inside of TouchDesigner in just a second. So one thing that we can do now to at least start visualizing this in TouchDesigner and make sure that we're on the right page or right track is to do a quick export and just export our X and Y's unlabeled just as points that we can then visualize. So the reason that I like using notebooks is because it makes it really easy to iterate and do some of this more ad hoc stuff in a way that doesn't really kill the workflow at all. So what I will do is, let's say, export XY is going to be a data frame, and it'll be double list, and we'll just grab X and Y, export XY.head, make sure it's working right. It is. Export XY dot to CSV, and this will be all stations dot CSV. All station normalized locations. So we can run that, and we'll see that we now have a all stations normalized locations CSV in our same directory, and this has all of our stations in it. So now we just want to get a TouchDesigner project going. So I'm going to navigate to this folder, the one that I created and am working within. Have it here. I will just create a new TouchDesigner project. Right here, we'll call this Global Bikeshare Data, and I will open it. Now I'm going to clean up my workspace a little bit. I'm going to add a new folder. I'm going to call this Python. I'll drop my sandbox notebook in there. Whoops. And then I'm going to create another folder. I'm going to call this Data. And I'm going to have my output in there. I can also update my path to point to this data folder location. And now I have a nicer setup. And we can open TouchDesigner. Now I can use a file in chop, and I will point this at my root data, grab this data file, whoops, file in dat, not chop. I see this file in dat that has our X and Y, and it has 1912 columns. So we can easily make this a dat using channel per column. First column is names, and first column is ignored. So now we have an XY array just like this. Now we can just set down a very quick rendering setup. So we'll use an Add SOP, then we'll use a convert SOP. We'll convert that to a particles per point. This is the same process that I used in my rendering point clouds tutorial with the OpenStreetMap data. We can drop down a geometry. We can drop down a point sprite, then a camera, a light, render, Alt-N to add a null, and then we are cooking. We can then add a null after our chop, call this all station pose, turn on instancing, and then instance. Now, pop this up in resolution a little bit, and maybe set our camera to ortho and the center to bottom left. And we can just do this pre-transform with 0.5. That gets us pretty much centered. Obviously, we can start to see that the points are indeed there. I'll put this over a black background to make it a little bit easier to see. And just like that, we have our points, all of our stations visualized. That also indicates that our normalization is working correctly, and that the data we're pulling is right. So, well, we'll get into the fine tuning of the visualization a little bit later, but now we can at least see that things are working right. And I'll save this touch program so we have a basis in TouchDesigner to work on too. Okay, so what do we need now? Well, we have all of our station information, but what I am also interested in is the real-time information. So we want to know what stations are starting or ending rides at any given point in time, so that we can use that information to make some pulsing or particles or whatever you are interested in using as far as the actual visual effect. So to do that, we're going to need a separate function. And the separate function is going to be pulling the station status information. So our station status is here. And this is the one that will show us how many bikes, e-bikes, and docks are available at every location. And the stations are just indicated by station IDs here. So I guess one thing that we probably want up in this column, or sorry, in our station information, is going to be the name, just so it's more readable for us as a person. So we can just add name. Oh, looks like my Python restarted. I just have to run my cells again. And we can see that now we have the names of each station added here. We have an error on our export. Let's see. So because I added this subdirectory, we can just prefix this. Oops. We can just prefix this with our ... and now works. We can see our data is being updated here. Okay, so we have our station name. Now we need our real-time data, so we'll hit B again. And actually, what I'll do is just copy this function. Get real-time updated data for ride starts and stops. And then I'll call this get bike starts. Actually, maybe I'll call it get bike changes. Then we can simply take this station status and replace our station information in the URL with our station status. Now, we're probably not going to be able to use these functions because I don't think the columns are going to be the same, and we're not going to have lat and long. So I'm just going to run this function as is and see what happens. Okay, so it actually does seem to be working. We have bikes available, e-bikes available, station ID, and some other information. So we can grab the station ID, and then we can ask for the number of bikes available instead of the name, because it doesn't have the name here, the number of e-bikes available, number of docks available, and we can also probably add a flag for station status. And then I'll keep the legacy ID in there, again, just in case we need it. So we can get rid of all of this. And now we can see our station ID and all of the information that we're grabbing. So whether it's active, how many bikes are available, how many e-bikes are available, and how many docks are available. Now, this is just a point in time, so it doesn't actually tell us starts and stops. To do that, we need to calculate it ourselves using comparisons from one time to another. So what we'll do is write a little program that's going to query the station status API. It will save the responses from time 1. It will then query it again, save the responses from time 2, compare those two responses, looking at each station in time 1 and time 2, and then see if there were any stations that have different amounts of bikes. So another thing we probably want is to be able to get our latitude and longitude on here. And so we can do that by merging these two. So I guess we can call this, actually, instead of get bike changes, get station, well, I'll call it get bike changes. No, we'll call this get station status. And then we can write a new function that we will call get bike changes, and this will old data. What this will do is take in an old data, specifically an old data frame. It will then call get station status again and compare the two data frames. We'll deal with the latitude and longitude later. So first we will create a empty array called changes. Then we will find the updated data. The updated data we will access by using our get station status function. And we can take a look at that using print updated data dot head, and then we'll just call our function and we'll get an error because we didn't pass an argument. So I will add a default to this argument, and that will be none. Get station status is not defined. I need to run that cell. I didn't run it after I renamed. And now we can see that, yes, we do have our updated data, which is getting pulled. So now what I need to do is compare these two. So if we don't pass in any old data, that means that we are calling this for the first time, which means that we probably just want to call our updated data get station status function and just return the results. So if old data is none, we will simply turn our updated data. And we can sort that by the index. One thing that I forgot is that we will want to, on our data frame, set the index to station ID. That will help us in the future. And I'm going to add that to both of our functions. Set index, station ID. So we can run that. We can run that. And now things are working. So we're just returning our updated data. And we can also return our changes, which is right now just an empty array, which is fine. So if our old data is not none, it means that we are passing in an old data frame, and so then we want to do the comparison. So we'll say UDF is going to be our updated data dot sort index. The reason that we have sorting the indices is so that we can compare row by row and know that we're comparing station by station. So that's why it's important for us to sort the index. And then our old data frame can be old data dot sort index. And that is also why we needed to have the index be set to the station IDs, which actually might not be working the way that I want it to. So we can check. Set index, station ID. Okay, so then for whatever reason, it's not working here, but I will just return this data frame with the index set to station ID. And then we'll see what happens. Okay, so that is working well. And I will just do the same thing here. Just like that. And now we can see that our station ID is indeed our index, which is great. So now I will say our old is going to be get bike changes passed with no argument, which will just pull the most updated data. And then our updated can be get bike changes, and we'll pass old. Turn I guess we don't want to return anything right now. We first need to compare the two of them to see whether or not there are any changes. So to do that, we'll go row by row. We'll say for I in odf.index. Let me actually say ID to make it a little bit more obvious. Print ID, and we'll see what happens. Tuple object has no attribute sort index. Right, because I'm returning both the updated data frame and the changes, I actually need to do this so that I'm associating this old with the updated data frame, and then this empty variable changes. And then we can say updated changes equals our getBike changes of old, which will then, well, right now it's not returning anything because we don't have a return statement in this part, but it will. And we can see here that we are printing out our IDs, so we can verify that the ID in the index is actually our station IDs. Okay, so now that we have the station ID, we can compare row by row. So if our updated data frame .loc, that's going to be for locating a row based on the index. And the column that we'll want for that is num bikes available. So if our updated value is equal to our ODF, old data frame value for the same location, which is the same ID and the same column, if those two values are the same, it means there is no change. Whoops. If values are the same, no change. This does ignore the case where there was a bike that is added and pulled out within the same time frame, but we're going to be looking at 5-second increments, so I'm going to just ignore those cases. So, if this is the case, we will simply pass, because if there's no change, we don't care. If there is a change, though, we're going to want to add a row to our changes array. So to do that, you can say changes plus equals, and here we can add our ID. And then we can return our updated data frame and our changes. So now we didn't get any output, but if I look at changes, or sorry, if I look at updated, we can see this is returning a data frame like we expect. And if I look at changes, okay, well, there were no changes in there. That's probably because we were hitting this at the same time. So, meaning we were calling getBike changes, filling up our old data, and then immediately calling the getBike changes, passing in this old data, which was resulting in identical data. So, instead, we can have this cell here. We'll run that. We'll add a cell below, and we'll say updated changes equals get bike changes of our, and then pass in our old data. So I'll run this. I will again hit B to add a cell, and now we'll look at changes. And we can see here that there's a list containing 60 stations, which means that 60 stations had a bike either entered or withdrawn from that station over that intermittent period of time. So the fastest that the real-time API URL updates is every 5 seconds. So the fastest that you should really call this is every 5 seconds. And then you get a list of all the station IDs that changed for each of those seconds or intervals. Now, to make this usable, what we also need is changes and the XY data for where those changes took place. So we could just call the station data, or get Citibike data. I should probably call this get station data. I'll run that function. We could just call that inside of this get bike changes function, but we probably don't want to do that because it will just require a lot of API calls that we don't really need because the station data doesn't change. So we can say, perhaps pass as an argument station information df. Then we'll use the station information data frame to pass in our updated or our station info from the first call, so we don't have to call it again. And then we will look up the XY coordinates for each of our changes. So we can do that by first creating a changes data frame, and then we will create it. And we will use set index. Actually, I don't even think we need to do that. We'll just add a couple more columns, and then we can add a columns array here. Station ID, which is actually all we need. I don't know why I added these 2 columns. Sorry about that. And then we can output our changes df. And we'll have to put our station info before this old data parameter simply because it has, we need to have the keyword arguments at the end as a Python thing. Okay, so we'll run that. We will run our station data equals get station data, and then we'll pass station data into this function, which worked. Now we can wait a little bit and run our updated. I didn't wait long enough. And we'll see our changes in data frame format. Okay. wait a little bit longer. So what we need to do here is then merge two data frames. So I will first go up here and set the index of this new data frame on our station ID, and then we will create or overwrite our data frame using this merge function. So that's pd.merge, and we want to merge our changes data frame to our station info data frame. And we want to merge that on the column station ID, and then how we want it to be an inner merge. Okay, so I'm getting an error there, or not getting an error, but just not seeing any changes because I forgot to pass my station data into the second one. So if I do pass that now, I can indeed see that my changes data frame is being populated. In this case, I have 179 changes since the last time I called. And each change has the X and Y coordinates that we need as well. Now, if we really wanted to, we could calculate the difference in bikes available to be able to see which direction changes were. So, for example, we could say something like old bikes equals odf.loc id num bikes available. New bikes, and we'll change this to NDF, or sorry, UDF. And then we can add a column called new bikes minus old bikes that we can title gain loss. So if there was more old bikes than new bikes, it'll be a negative number, which will be a loss. And then finally, we can maybe just grab the columns we care about from changes. So we can do station ID, name, XY, gain loss. Station ID, name, XY, gain loss. So we can just run this again and see if it works. Doesn't quite work because I had this ID in quotes and I shouldn't have. Okay, so all I had to do is remove the station ID column since that was actually our index. And now we can see that our changes has just our station, the names, XY, and gain loss, whether that was a start, for example, here where it was a loss, or a gain where it was a ride end. So yes, now we have most of the pieces that will enable us to actually get this data flowing into TouchDesigner. So what we need to do now is do the rest of this outside of a Jupyter notebook, because our final step is going to be setting up a short function that's going to continuously call our get updates or get starts, get bike changes function every 5 seconds, as long as this program is running, and then send each of those updates to TouchDesigner via OSC. We can't really do like delayed run every 5 seconds type of stuff in Jupyter. So I like to use Jupyter to get all of the logic and functionality down. As you can see, it's easy to use to kind of view and process the data. And then I will create a new file, which I will call main.py. And I'll drop that in my Python. And here we can just start to port this over. So we'll copy and paste our imports. We'll copy and paste our utility functions. We can copy and paste our station info. We don't need to copy and paste this one since we've already exported. We do want our station status function, and we do want our bike changes function. Pair real-time updates to identify changes. Cool. So now we have all of this in a Python program. What we can do is write a short little function that will be kind of our main program. We'll put that here. Program. What this main program is going to do is initialize all data, save station locations to CSV, then every 5 seconds call API for updated station status and record changes, and then send all changes to TouchDesigner via OSC. So that's going to be our program, and we will start writing the rest of that program in the next section. So thank you for following me along so far. I appreciate the support from everyone, and I will look forward to seeing you shortly.